All right, good morning, guys. So let's continue to what we have been dealing with in our previous lectures, right? Again, just a quick recall, but mainly remember in our last class we started solving a little bit of exercises. So this is actually what we will keep on doing now. And then we will move on. Again, in this class, I'm going to introduce you a little bit of more concepts and again, some sort of math concepts, but you'll see that they will be very useful in the future. But remember what we have learned in our previous classes, right? So we were dealing with, now we figured out what, under what conditions, for instance, we can get these nice, smooth indifference curves, right? Now you guys know. And we know that, right, so for these, in order to get these indifference curves, we needed at least a quasi-concave, strictly quasi-concave utility function, right? So that we could have these convex indifference curves. And remember, what did they mean? If you need to tell your grandma these strictly convex indifference curves, what would you tell her? That, does it mean that she would prefer, let's say, having, I don't know what your grandma likes, but, I don't know, let's say she's cool, she likes pizza and such, right? So what does that mean? It actually means that she would prefer, like bundles which had very little pizza and lots of drinks, or really, little drinks and lots of pizza, or some sort of a more balanced ones. Balanced ones, right? That's what we said. This is how we could interpret the actually this strictly convex indifference curves. We also had other, interpretations. Remember, we said that along this indifference curve, what's happening to what was the marginal rate of substitution? What is marginal rate of substitution? Remember, we said. Exactly, so that's the, the definition and sort of the intuitive definition we would say, but more, what did we say? In math, it was corresponding to what? In terms of math? It was basically, but we said that it was what? The absolute value of the slope of the indifference curve, right? So these were basically, right, like here, the slope here is the marginal rate of substitution at that point, and marginal rate of substitution at that point. And we said that along this strictly convex indifference curve, what's happening? Marginal rate of substitution is decreasing, right? As x increases, MRS is decreasing, right? And I remember in our last class, we actually figured out some other thing about MRS. What was it? So remember, we proved that apparently this marginal rate of substitution is equal to, right? So we said that it's equal to the ratio of the marginal utilities, right? So remember, we said ux, uy, right? And then we actually said that, so these were basically the partial derivative of the utility function with respect to x, partial derivative of the utility function with respect to y. Basically, these were marginal utilities. So it means that if I consume one more unit of x, but if I hold the amount of y constant, but if I consume one more unit of x, how would this contribute to my utility, right? And then we said that this marginal utility is most of the time what? So is it positive, negative, equals to 0? What did we say?
It's positive but tending towards 0.
So it's actually, let's say that most of the time this is positive. What does it mean? It means that, right? So it means that if you add one more x, it contributes positively or negatively to your utility. Positively, right? It adds up to your utility. And we said we link this with what? Right? So we said that, remember, we could have some properties of our preferences, which was more is better. And you see that if you need to express it in terms of utility or in terms of math, this is what you would say, right? And then what else we said? So we proved this, and then we learned something saying that, right, so this utility guy, right? So this utility guy does it matter, for instance, I like multiply everything by 10, or if I multiply everything by 100? No, right, you said that, oh hocam, all that matters is the order, right? But we said that it should keep the order, but what kind of transformations did we allow? For instance, if I want to represent the same preferences, so am I allowed to, let's say, represent the same preferences using actually some sort of a utility function like this? Suppose I have my utility function like this, but I claim that I'm going to, like assign all those bundles not to that number, but the square of that number. Do you think it's allowed? Yeah. Yes, right. What did we call this when we're taking positive monotone transformations, right? But was this allowed? So is this, remember, was this allowed? Logarithm was allowed as well, right? So how are you checking that it was a positive monotone transformation? Remember, you were taking the derivative, right? And then, so here you can actually call this function, you can call it, let's say, h of u, right? And here h is basically, so you put h of u, so basically it's u squared, right? So you actually check this h, right? So, and then we said that, fine, is this allowed? Can I do this? No, right? Because you said that, hocam, it's going to change the order. That's not allowed, okay? So remember, we also showed that even if you take the positive monotone transformation, MRS was it changing? It wasn't, right? So it's actually because, remember, you can actually, like, we proved it. So MRS was giving whatever, no matter, so it means that it doesn't matter how you measure utility, as long as it keeps the same ordering, it's going to give the same MRS, right? So it's going to be exactly the same, right? So that's what we said. That's why we can, sometimes when the function is actually a little bit hard, in order to figure out the indifference curves, we can take a positive monotone transformation, right? You're going to see later when we do utility maximization, if that utility function is hard, you can take a positive monotone transformation and try to do the maximization there. Okay, so you'll see. So this is actually very important. So this is what we have seen. And remember, yes? In English.
Why indifference curves are defined, or are they defined convex? Why cannot they concave? The reason is it violate rationality?
No.
Yeah.
So actually, that's a very good question. So remember, we linked some of those, concepts to rationality. Remember, I put down when we call those agents rational, right? But do you remember? Did I write down convexity there, right? So what were those? Do you remember? They were completeness, reflexivity, and transitivity, right? So these were related to rationality. We said that even continuity is not, related to rationality. These are all extra assumptions, okay? So these are like, it doesn't have to be, okay? So these convexity has nothing to do with rationality, okay? So convexity, you're going to see that later on, we need these nice convex forms. Why do you think we need them? So actually, you'll see that these we need, even though we gave some sort of an economic interpretation, we need this so that we can take derivatives, right? Otherwise, if we had like these weird functional forms, it would be hard for us to deal with them, okay? And basically, so you'll see that this is going to be the case. And also, we wanted the utility function to be, at least quasi-concave, so that, like they're going to be a maximum. A maximum will exist. But it's going to be a constraint maximization problem, so it will exist anyways. But you see that we need these guys so that we can define derivative, right? So like, for instance, you can define MRS here, right? If I had a weird functional form like this, which we will see today, is derivative defined everywhere? No, right? Where it's not defined where? At the kink, right? So we don't know. So it's actually, if we would like to use math, if we want to use derivatives, you'll see that we need these guys, okay? So that's why, actually.
If it's a concave function like this,
Huh.
can't we take derivatives?
Exactly, so it could be the case. So we'll see, okay?
In this case, can indifference
Curves be
can concave?
it can be concave. You can be a weird person, It doesn't even mean that you're a weird person, right? It can be the case, right? So, but then actually the derivative is also defined. But you'll see that when we have concave indifference curves, and actually I can tell you, we need these so that we would have an interior solution, okay? So if we have a concave indifference curve, you'll see that we're going to have a corner solution, okay? So you'll see. So basically, yes?
Can we relate the convexity with the scarcity? Can we relate the convexity with the scarcity? In order to gain more benefit of the other good, or in order to buy other good, we have to give up the other good.
Yes.
Of limited good.
Yeah, but but we said that, remember, it's actually related, so that's a good question. It's actually related to the fact that this has a negative slope, okay? So not the fact that it's convex, so because it could be convex but could be up positively sloped as well, right? So, but this is here, scarcity is actually related to, like the fact that these MRS is actually, or the slope of the indifference curve is actually negative, okay? So that means in order to gain, like to keep the utility level the same, you have to, if you are giving up some good, you have to compensate the consumer by giving the other good, right?
In case of concavity, the scarcity problem will not be there, right?
No, but if they were concave, suppose you had something like this, right? So you see that again, right? So there is also the trade-off, right? Again, they're negative, but the slopes are not decreasing, okay? Okay, so this is basically it, right? So that's what we have said. And then remember, and then I actually told you something else. What was this? So you guys told me that, oh, hocam, this is related to more is better. And then you told me, and then we were discussing something like this. UXX, or you can actually call it like this, right? So what is this? What did we say? This is the second derivative of the utility function, right, with respect to x, or it's the derivative of the marginal utility. So we said that this is, right, so remember we said that this could be diminishing, right? It doesn't have to be, but mostly we actually, if you assume that there is diminishing marginal utility, which means that if you have, like let's say you keep eating chocolate, now the extra chocolate bar is going to add up to your utility. It might be the case that chocolate is a good, right? All the time it's going to add positively. More is always better for you, for chocolate. But what does this say? Each time it's going to add a smaller amount to your utility, right? So that's what we mean by the diminishing marginal utility, right? And then we said that we try to link this marginal utility, right? So diminishing marginal utility and diminishing marginal rate of substitution. So these guys were the same or not, right? Were they the same? No, right? So remember we talked about this. So just remember, so diminishing marginal rate of substitution, remember it was equivalent to the fact that this indifference curve was strictly convex. But that then we checked this, and we know that when it's strictly convex, it also corresponds to the fact that utility function is at least, right, strictly quasi-concave. We checked the condition for quasi-concavity, right? But if you have these guys, it didn't necessarily imply that you have this guy, right? So remember, so this is what we did in our last class. And then we started solving some problems, and your friends kept asking about concave indifference curves and such. So let's see. Remember, I think we did one example. Now this is going to be the second one, okay? Examples, continue it. So suppose we have a utility function like this. It could be you don't care. You don't have to know, like the type. Apparently, for instance, this is a hyperbolic paraboloid, okay, but we don't care, okay? It could be anything. You can be anyone having these representation. Now, suppose I asked you, like whether indifference curves are convex or not. What should you check? Right, so remember those four, circles, like four concepts that I said they're all equivalent to each other. So if I want to check whether, for instance, this utility function would lead to strictly convex indifference curves, what should we check? Should we check that convexity condition, which was ugly? No, right? We said there's an easier way. We can check MRS, right? So let's actually check. So shall I take a transformation here? No, right? It's easy, right? Remember, what was MRS? MRS was equal to u of x, u of y, right? So if I can take the derivative easily, why should I be taking the transformation? So what is the derivative with respect to x here? 1 plus y, right? And what is the derivative with respect to y? 1 plus x, right? Okay, what's happening to the marginal rate of substitution as x increases? So the formal way of showing this, actually, you should do this, right? So you should be taking the derivative of the MRS, like with respect to x, and then, but you should keep in mind that whenever you take this derivative, you should always keep in mind that, right, you're on this indifference curve, right? And on the indifference curve, you keep utility level constant. Therefore, this y guy is a function of x as well, okay? But just, like this is actually a more formal way of looking at it, but it's okay for the time being for us that you can actually make the following, argument. Remember, what did we say? So we actually said that when as x increases, what's happening? As x increases, so we said that, so as x increases, okay, so this guy is going to cause this guy to fall, right? And then, but we said that first, the denominator is going to, right, increase. But what's happening also, is that the only case why, MRS is going to be diminishing? No, right? Because we also said that when you increase x, y is decreasing, right? So that's why this overall MRS is actually decreasing, right? As x increases. So you should actually be, so this is, informal way of saying the same thing. But formally, you should check this, but you should always consider this y as a function of x, right? When you take the derivative, if you want to take, show it using, like taking the derivative of MRS with respect to x, okay? But for this course, this is enough, okay? So as x increases, we know that, so there is denominator, we know that increases, and you know that y would decrease, so numerator decreases. So overall, right, MRS decreases. This we know, okay? And then you can actually say that because there is diminishing marginal rate of substitution, indifference curves are strictly convex, okay? So that's what we could say. You see, I don't know how to draw these indifference curves, but I can actually say whether they are strictly convex or not, okay? So another example. Yes?
I didn't get why exactly why is decreasing.
So this is actually, so remember what is MRS? So it's the slope of the indifference curve, right? So this is y, x. So you see, as I increase my x, right? If I go this, my y should decrease, right? If I want to keep the utility level the same.
Why is output too?
So y is the other good, right? X, y. If you keep utility level the same, if you change x, this y is going to change as well, right? Because you want to keep the utility level the same, because you want to figure out whether along this indifference curve, as x increases, whether marginal rate of substitution decreases or not, right? And which means that you have to keep utility level the same. So if you increase x, you should be decreasing y, right?
Does this apply in all the conditions, even in the weird indifference curves?
So we'll see. So let's actually, it doesn't have to be the case, right? So let's see another example. Okay. Yes.
If the indifference curve is concave,
Okay. So I'll do that example. Okay. They kept asking me. Now here it comes. Okay. Now utility xy. Okay. So let's have this. So now I ask you. So whether indifference curves are convex here. So let's see, right? First of all, so I have to check MRS. This I know, right? Now, do you think it would be useful for me to take a transformation? Yes, right? We might. I mean, you don't have to. You can say that, oh, hocam, I can take this derivative. It's easy. Or if you want, you can take a transformation. What would be a smart one, right? So we take the square of it, right? U of xy squared. And you know that square is a positive monotonic transformation, so it's fine. So this is going to be what? So we said x squared, y squared, right? Now, so I know that, so this we proved. I can just check, right, the marginal utilities of this utility function, transformed one, right? So what is it? If I take the derivative with respect to x, 2x divided by 2y, right? So what is it? X over y. So let's see what's happening. Again, what's happening to MRS? As x increases, we know that, right? So x will increase. And what was happening to y? It was decreasing, right? Because remember, we're on the indifference curve. So if x increases, y should be decreasing to keep utility level the same. So this guy increases, this guy decreases. What's happening to MRS? It increases, right? As x increases, again, you have these two reasons, right? X increases and y decreases. So overall, MRS increases, right? Okay, what's happening? Do we have strictly convex indifference curves here? So we'll see, right? So it doesn't seem like, right? So, and you should be suspicious, right? If I want to draw, remember the very beginning, how did we draw the indifference curve? We said that, oh, we're going to set this equal to, let's say, 5, right? Suppose I set it equal to 1. How does this look like? It's the unit circle, right? So it's, if I want to draw this indifference curve, but we always work in the positive quadrant, right? So then it's something like this. So if it's, right? Let's say if it's 1, right? So this is x squared y plus y squared, right? So the indifference curve. So we know that you see the slope of this, what's happening to the slope of this indifference curve? It is actually the slope, I should be absolute value of the slope of the indifference curve. It is increasing, right? So this is, you see that it's actually concave, and you see that we figured out that marginal rate of substitution is not diminishing, okay? So you see that later in this type of concave indifference curves, they are allowed, you can have that, okay? That's perfectly, it doesn't say anything about that you're crazy, you're not rational or whatever, right? But it's actually going to see that these are not going to lead to interior, what we call interior solution. In these cases, you'll see that the optimal point that you would like to consume would either be here or here, okay? So you'll see, okay? Later, either you'd be consuming only x or only y, okay? So you see that here we have, so increases, so here we know that indifference curves are not convex, okay? So here you have concave indifference curves, okay? If I had drawn the other one, let's say at 2, it would have been like this, right? So you have this concave indifference curves, okay? So this is basically the case. Now, So you see that we don't, even though I showed you that ugly condition, you never have to check that ugly condition, right? You can always check MRS, okay, to figure things out, what's going on. Now, what we will do is that this is very important. We're going to see some utility functions, okay, which would represent some specific preferences, okay? So this is what we would actually do. So let's see. And you'll see that both in consumer theory and also in producer theory, firm theory, we're going to use these functional forms a lot, okay? So it's good that you know them by heart now, and then so that you will be actually safe for the later portions of this course, okay? So let's say some utility functions, okay, for some specific preferences. So the first type of utility function that we're going to introduce, it will be called Cobb-Douglas utility. And now you'll understand why. So when you draw the indifference curves for this Cobb-Douglas utility function, you would have these nice shape that we kept talking about, okay? You know those indifference curves that I kept drawing, those nice ones? So for instance, Cobb-Douglas utility would give these kind of nice utility indifference curves, okay? So basically, so they would have this nice familiar shape we have seen until now. And it would be, so the utility function, which is going to give these nicely shaped indifference curves, is x to the power alpha, y to the power beta, okay? Alpha is positive, beta is positive, okay? So this is called Cobb-Douglas utility function. Do you know why?
Cobb and Douglas.
Yeah, actually Cobb and Douglas, they're two guys, right? So actually those were the ones who figured this out. So basically, but not in actually consumer theory. You know what they did? They looked at, production function for US actually data. And it turned out that this function, you're going to see that in firm theory, instead of good X, good Y, we're going to put here capital and labor. And it turned out that for them, this functional form was the one that fit the data the best, okay? Production, in terms of production function. So this functional form, has been used very intensively. So, and it's very, you'll see it's very convenient. It would be the easy case. Whenever you see Cobb-Douglas, you would say that, oh, that's Cobb-Douglas, that's easy, okay? Because it's going to give these nice case and everything will work very smoothly, okay? So this is basically what actually, as we said, that these researchers, found this use this functional form a lot in terms of productivity, sort of like production functions, okay? So, but for instance, if alpha is relatively too high compared to beta, what do you think it means? What does alpha and beta show? If you tell your grandma, she doesn't know alpha, beta, right? She doesn't know what exponential means. But what would you tell her? If alpha is greater than beta, what would you tell her?
When we want to add one more x, how much y we should give?
No, but even much easier. So this is actually not a very hard question, yes.
Probably X is preferred.
Huh? So like not more preferred, but like do you, right, grandma, you like X more than, right, Y, right? So you can actually have this sort of interpretation, right? So it's actually, these guys show the relative importance of these goods, okay? So even though, so for instance, if alpha is greater than beta, okay, relatively, and too high compared to beta, where do you think these indifference curves are located? So that's another thing. So these, do you think these would be closer to x-axis or closer to y-axis? Actually, if you can try, but if you know, like if you have an alpha greater than beta, okay, then these indifference curves are more, you know, towards the x-axis, and you would see that these indifference curves, if beta is greater than alpha, they would be, you know, like located more towards this axis, okay? So you can just give 2 examples and try, okay? Now, fine, what about in Cobb-Douglas utility, what about MRS? Right, so what is marginal rate of substitution? So we can actually compute, right? So we know that it's going to be u of x divided by u of y, right? So what is it? So if I take the derivative with respect to x, alpha, right? X to the power alpha minus 1, y to the power beta, and this is going to be the derivative with respect to y. What is it? Beta times beta minus 1, right? X to the power alpha, right? So this, and then, you know, like here x will stay, here y will stay, right? And then this is going to be alpha over beta, y over x. So apparently, MRS is this in the Cobb-Douglas case, okay? So this is basically the case. So what else we can say about Cobb-Douglas? You're going to see that we will be using this a lot. Now, I'm going to give you what we call like 2 extreme cases, okay? So you see that this Cobb-Douglas is nice. The other one is going to be, you guys would tell me, I'm not going to tell you the name, okay? Now, suppose I'm going to have a utility function like this. So alpha x, beta y, okay? Alpha greater than 0, beta greater than 0, okay? Suppose I have a utility function like this. So what kind of indifference curves this would lead to? Linear, right? So let's write this. So linear indifference curves. So basically it's right, so this is actually, so the linear indifference curves, right? So that's what we said. Fine, so let me draw this. Okay, so how will I draw these indifference curves? Always keep in mind that you see that we have many definitions. We can look at marginal rate of substitution. We can use the formal, you know, like the first definition of MRS, right? You can either say, oh, it's the absolute value of the slope of the indifference curve. You can just try to get the slope of the indifference curve, or you can use, you know, like it's the ratio of the marginal utilities, right? You see that we have many definitions. And what else, right? So basically, so like in order to draw or you can draw the indifference curve to figure out what's going on. And remember, how were we drawing the indifference curve? We were setting this guy, u of xy, alpha x, beta y, to some number, right? And then we were trying to, let's say this is u0, and then we were trying to get y in terms of x so that I can draw it, right? So that's what we were doing. So basically it's going to be beta y equals to u0 minus alpha x, right? Y equals to u0 divided by beta minus alpha over beta x, right? So if I want to, for instance, figure out MRS, what would I say? It's the absolute value of the slope of the indifference curve. What is the slope of this indifference curve? So this is my indifference curve, right? Right, minus alpha over beta. So you would say that MRS is, hocam, not minus, minus, right? So it's going to be alpha over beta, right? Or you can say that, oh, hocam, I want to get MRS using this formula, ux over uy. You see that sometimes, not here, but you see that it's not going to be the indifference curve. The derivative might not be defined, right? Or the utility function might not be differentiable, okay? So then how are you going to talk about MRS, right? Then you cannot apply this definition, but you can actually try to figure out, like what's going on there, right? So what is this ux over uy, MRS? We said that what is the derivative of the utility function with respect to x? Alpha. And what is the derivative of the utility function with respect to y? Beta, right? So either you write this or you write this. We figured out that MRS is alpha over beta. What does that mean? MRS is constant, right? Compared to the Cobb-Douglas case, remember, there it matters how much y and x you have, right? So wherever you are, apparently it matters whether you're here or here or here, right? MRS changes. But in this one, MRS, it doesn't change, right? Fine, so let's actually draw this. So this is y, this is x. Now you guys think, do you think it means? Remember, what did MRS mean? It means that in order to have one more x, how much y I should be giving up, right? And here it's going to be how much y should I be giving up? It's always the same, right? Apparently at any point. So if I want to draw my indifference curve, as you said that, hocam, these would be linear, right? So the slope, as you said, is hocam. So slope is going to be minus alpha over beta. That's what you said, right? So this is, this is the case, right? So if you can put the, intercepts and such, but doesn't matter, okay? So what do you think we should call this? Right? These are actually called, so if you have these type of linear indifference curves, you see that we call them perfect substitutes, right? Because you can always substitute one guy at, like exactly the constant rate for the other guy, right? So we call these perfect substitutes, okay? And for instance, suppose, let's say alpha and beta, they're equal to, so let me give you examples. For instance, for some people, not for me, but it's actually Pepsi Cola and Coca-Cola. Okay? So this is basically, for instance, let's not say versus Pepsi and Coca-Cola. So for instance, what do you think alpha and beta if you have Pepsi Cola and Coca-Cola? What do you think they are? Right, probably equal, right? So for people, for me, for instance, I prefer Pepsi more than Coke, but right. So, but for some people, it might be the same, right? So it's actually, so alpha and beta, they are the same. It doesn't have to be 1-1, but it could be 2-2, right? But we actually say that Pepsi Cola and Coca-Cola, you see that you can always substitute Pepsi Cola for Coca-Cola at the same rate, right? It doesn't matter. Or for instance, you can actually think of, that at Kennedy, the Kennedy, like street, like at Bestekar, at the intersection of Bestekar and Kennedy, there is a Shell and there is a BP, right? At least as far as I remember, they were there, right? So gas from Shell and gas from BP, right? For me, I don't care, right? It's the same gas. Either I buy it from there or either I buy it from there. So I can substitute, let's say, 1 liter of gas from Shell with 1 liter of gas from BP at the same rate. And as you said, that the slope might be, in that case, -1, right? So you can actually think of many examples that you can easily substitute one for the others, okay? But do you think it's always have to be at a rate 1? 1. So suppose I put here another example. Suppose I put here, for instance, 1 Turkish lira banknote, and I put here 50 Turkish lira banknote. Do you think these guys are perfect substitutes? Yes. Yes, but don't think that perfect means it should be, 1, 1, but it means that you can always substitute one guy at a constant rate for the other guy, okay? So perfect substitutes. So what is this? So what do you think the slope should be? You would be, like if I want to get 100 Turkish liras, I should be giving up how many? 2, right? So what is it? Then slope is minus 2, right? So it doesn't have to be minus 1, right? In order to have 100 Turkish lira, it's okay. You can give up 250, right, Turkish liras. That's fine, right? So they're the same. You can always exchange them, right, at a constant rate, okay? Huh? They don't?
If you go somewhere and probably ask for 250 TL banknotes instead of by giving 100 TL, so probably not good because 50 TL banknotes are more easy to circulate, I guess.
So, I mean, he's right. It could be the case that one of that 50 Turkish lira banknote has a signature on it, like, or whatever. It might look newer and such. Of course, so there could be all sorts of stuff. But, mostly, I think if you give, right, like 100 Turkish lira, they might give you 2 in exchange. Or if you give 2, they would give you, 100, right? So most of the time. But of course, these are very extreme cases. So it's hard to find examples. But 50 Turkish lira banknotes and 100 Turkish lira banknotes. Okay? So this is basically what we call perfect substitute. So what is important about perfect substitute is, as you see that the MRS is constant. Okay, so and then if you want to look at the utility map, you would have something like this. Right, so these indifference curves are linear and they're parallel. Okay, so let me ask you this and then we'll just give a break. So here, so what's happening to MRS? So do I have diminishing MRS here? Right? So as X increases, I know that X increases, but to keep utility level the same, there's this trade-off, so Y would be decreasing. So this guy overall is decreasing, right? And what about perfect substitutes?
No change.
It doesn't change, right? Can I say that there is strict convexity here? Remember, what did we say? Strict meant what? Strict, so like, remember strict meant? No, what did I say? No flat portions, right? So, right, so strict means that, so this is convex as well. It's linear, right? So it's well convex. Here, it's strictly convex. So if you see that MRS is diminishing, here, it's convex. But it's not strictly convex. So we lose strict convexity here, right? And you see that MRS is not diminishing, okay? So you see that it's actually important. Here, you're going to see that later on. Again, we cannot guarantee all the time a nice interior solution, okay? But we'll see, okay?